Hello viewers, welcome to my channel and thank you for watching the videos. In this video I will discuss question number 5b of mathematics optional paper UPSC 1992 complex analysis question of 20 marks, and here we have to integrate along a suitable contour. We have to evaluate 0 to infinity cos mx upon x square plus 1 dx. Now this comes under the definite integrals, that how to evaluate definite integrals. So first thing I would like to tell you that there are three type of cases. First is minus infinity to infinity fx dx, and fx is a rational function. In this what we do, we take the contour minus infinity to infinity, half upper circle we take, and radius of that circle is capital R we are taking, and the semicircle circumference we take as tau, so along that curve, and this will be the contour. So along x-axis it is from minus R to plus R, and semicircle tau above the x-axis having this line as diameter. Minus R to R is diameter. And when r tends to infinity, fx is an even function, and this can be used to evaluate this integral 0 to infinity fx dx. Now second type comes when we have 0 to 2 pi and function is of this form. G is a function of sin theta and cos theta d theta. So in this case g, which is a function of sin theta cos theta, is a rational function of sin theta and cos theta. Here we take z is equal to e to the power I theta, and sin theta we take z minus z inverse, or z minus z inverse upon 2i, and cos theta is z plus z inverse upon 2, and dz becomes I e to the power I theta d theta, or we write d theta is equal to dz upon iz. In this case what we are doing, we are converting into a unit circle. So it becomes integral equivalent to closed integral over unit circle fz dz. So, and center of this circle, which is unit circle, will be origin. Case 3 is when we have minus infinity to infinity integral we have, and fx, which is a function of cos mx and sin mx dx, and fx is a rational function. Here what we do, we take closed integral c, contour is same, that is upper half semicircle, and fz e to the power imz dz, this we take. So closed integral c fz e to the power imz dz, and we integrate it. Further, there are two important theorems which we use to apply or use to integrate these contour integrals. First is, it is often necessary to show that integral over gamma, that is the tau or gamma, we say whatever, which is semicircle circumference fz dz, and integral tau e to the power imz fz dz approach 0 as r tends to infinity. This is often necessary. So what we use to show it 0, first theorem is, there are two theorems. First is, if mod fz is less than equal to capital M upon capital R to the power k, for z is equal to r e to the power I theta, where k is greater than 1 and m are constants, then if tau or gamma whatever is the semicircle, then limit r tends to infinity integral tau fz dz is equal to 0. So this is first statement. And second theorem is, if mod fz is less than equal to capital M upon capital R to the power k, for z is equal to capital R e to the power I theta, where k is greater than 0 and m are constants, then if tau is the semicircle, limit r, capital R tends to infinity, integral tau e to the power imz fz dz is equal to 0. So these two theorems we will be using, and the case is third case which we will be applying for this. So now we come to the question. These are the basic requirements which I have told to know that how to solve these type of questions. Now to solve this question we will be using the third case of integration, and the theorems we have discussed two theorems we will use. So x-axis we are taking minus r to r, and the perpendicular is here, y-axis it's going through origin. So this is y-axis and this is x-axis. Here we have taken minus r to r on x-axis, and tau is the semicircle circumference. So the whole contour we have defined by gamma, and semicircle circumference by tau. Direction is anti-clockwise, and radius of this circle is of course capital R. R we are taking Z we are taking capital R e to the power I theta. Now here we can write down fz as in case 3 I had told that we can write down e to the power I mx upon z square plus 1. So m is there, we are writing I a z upon z square plus 1. So we break the whole integration in two parts. Limit r tends to infinity, gamma fz dz. Gamma is whole control, the x-axis and the semicircle circumference. So minus infinity to infinity e to the power iax upon, because on x-axis we will write x square plus 1 dx. Tau, here limit r tends to infinity, and it is on semicircle, so we will write z e to the power az upon z square plus 1 dz. Now as I said that we have taken z is equal to capital R e to the power I theta, and fz we have taken this e to the power iz upon z square plus 1. Now if we take only 1 upon z square plus 1, so this becomes, and mod of complete we are taking, mod of whole. This is basically is equal to is equal to 1 upon mod r square e to the power 2I theta plus 1 theta plus 1, and mod of this will be less than equal to 1 upon mod r square. Now see, mod now on in denominator on this term 2I theta and minus 1, because this is less than equal to minus 1. So this term is less than equal to, and e to the power 2I theta mod will be 1. So we can write down this as 1 upon r square minus 1. It means we are writing mod fz, that is 1 upon z square plus 1 mod, is less than equal to 1 upon r square minus 1. And if we cross multiply, it becomes mod z square plus 1 is greater than equal to r square minus 1, when, because this is less than equal to, and this becomes r square minus 1 in denominator. So when we cross multiply, this becomes this much on the circumference of semicircle. And we know mod e to the power iaz is equal to e to the power I a, z have been kept r e to the power I theta. I square gives -1, so ar sin theta, and theta is here 0 on this axis and it is up to here, that is pi. So theta is moving from 0 to pi. Theta lies between 0 to pi. It means this mod e to the power minus ar sin theta is less than equal to 1. So now we write the complete fz, that is e to the power iaz upon z square plus 1 integral tau dz will be, because this mod we have written less than equal to 1, this we have written r square minus 1, so r square minus 1 is there and 1 upon and integral tau dz, and that is what the circumference of semicircle, that is 2 pi r by 2, that is pi r. So this is the integral, the mod of this. Now we have to find out the integral limit r tends to infinity tau e to the power iaz upon z square plus 1 dz. This we have to show it is 0. So we got this term. Now we write dz as this I r e to the power I theta. We can differentiate it. We can differentiate z and can get this. So when we put in this, it becomes this. Suppose we are not thinking about this right now. We write it is equal to limit r tends to infinity integral. This whole term has come as less than equal to as pi r upon r square minus 1, and it's in integral side we can take it outside because we are going to integrate in theta and it is not depending on theta, both this is constant. So integral is 0 to pi because we are talking about theta, and this becomes I, then I also we can write here capital R, that also here, and e to the power I theta. So e to the power I theta I can write cos theta plus I sin theta, cos theta plus I sin theta d theta. Now if you integrate it, you will see that integration of cos theta is sin theta, and when we put limit sin pi minus sin 0, that becomes 0, and this I sin theta when we integrate it becomes minus I cos theta, and limit will be minus I cos pi minus I cos 0. So first becomes plus I, second minus I, cancels out, and it is 0. So we got this 0. So we have shown this second term is 0, this term is 0. Now we come to the first term which is here, and for that we will be using the Cauchy residue theorem, and Cauchy residue theorem says limit r tends to infinity gamma fz dz is 2 pi I sum of residues at of function e to the power iaz upon z square plus 1 in the upper half plane. Now we find out from z square plus 1 poles, and z square plus 1 is equal to 0 gives us z square is equal to minus 1, that is my I square. So z is plus minus I won't lie in this plane, in the upper half plane, so only z is equal to I is the only pole of fz. So we can find out residue at that. Residue is limit z tends to I and z minus I, because I is the pole, e to the power iaz upon z square plus 1 can be written as z minus I, z plus I, z minus I will cancel out. So when we put I is equal to z is equal to I, it becomes e to the power minus I square a. So minus I square is, it becomes e to the power I square a z. So this gives e to the power minus a, and in denominator only z plus I will give I plus I 2i. So when we write this integral is equal to 2 pi I into residue, 2 pi I into e to the power minus a upon 2I gives pi e to the power minus a. Now if we write e to the power ax in cos ax plus I sin ax form, we can break up this minus infinity to infinity cos ax upon x square plus 1 dx plus I integral minus infinity to infinity sin ax upon x square plus 1 dx is equal to pi e to the power minus a. And because second term this is 0, because when I discussed about first case, that is minus infinity to infinity fx dx, fx is a rational function, and when r tends to infinity, if fx is an even function, this can be used to evaluate 0 to infinity fx dx, but odd is then that is 0, so this is 0, so only first term is there, because cos ax upon x square plus 1 is an even function of x. So minus infinity to infinity gives twice of 0 to infinity, and that 2 we take on this side, 1 upon 2. So this is pi e to the power minus a upon 2, and this is what we had to